Welcome to Unit 21, Green's theorem. Let me start with a reminder of the fundamental theorem of line integrals. This is a special case when we have a closed curve and we have a vector field which is a gradient field. So we are in the plane today, PQ is a vector field which is a gradient field. So it's a gradient field. Then we know that this line integral, the work going around this closed loop, is equal to 0. So the line integral f dr is equal to 0. So let me just write that out, what this actually means. Say we parameterize this curve like this from 0 to 2 pi with the r of t times r prime of t dt. So that is this integral. That's, reminder, that's gradient of f of r of t times r prime t dt, and we have seen that this is d over dt f of r of t. So by the chain rule, and then we have, by the fundamental theorem of calculus, we have seen that this is actually 0 to 2 pi. So that's actually just by the fundamental theorem of calculus. This is f of r of 2 pi minus f of r of 0, which is 0 because they are the same. So that's a proof again of this important theorem. And we have also seen that this is has an interpretation as work, energy, and this total energy. We cannot gain energy in a gradient field by going around a closed loop. And perpetual motion machines try to beat this, implement a non-gradient field so that we have gain some energy by going around. So today we look at the case when we have not a gradient field, and we are looking what happens with this line integral. And the answer is given by Green's theorem, and that's the next section. Green's theorem is a fantastic result. We still are in 2 dimensions, and we have a region. Let's call it G because of green, to honor green, and also let's make it green. This is, maybe there's a hole even, so this region doesn't have to be kind of just like a disc. It can have a so this is this region, and what we have is, and that's important, these regions have a boundary, and the boundary, let's make it red. So this is the boundary. Let's call the boundary C. So G is a region in the plane, and the C is the boundary. And it's important that we orient this boundary. So that's something new. And we orient it in such a way that the region is to the left. So that G is to the left. So in this case, we would just go along like that. And on this side, we are going differently. So it's oriented so that the region is to the left. So what this means is we are walking, think about walking here along. So that's you walking here, the left foot and the right foot, and you're walking in this direction here, such that the left foot is on the region and the right foot is on the boundary. So that's what we call C. That's our region C. Also, that's part of C. And now what we can do is we can compute the line integral along C. So what we have, and that's now a theorem. So the theorem tells us that this line integral along C, f dr, this is now, we have seen if this was a gradient field, then the curl qx minus py was 0. Let me just remind you about that. We have seen curl, this is the curl of f. I just introduced this last time, but this is a very important notion here, the curl. And this curl is 0. If f is a gradient field. So in this case, so that points us to look at the curl here. And so what we have now is a double integral over g, and then we have the curl of f. So that's a theorem. Let me just write it down a little bit in more detail. So what we have is the integral, usually we have parameterized that from 0 to 2 pi, the integral from 0 to 2 pi, and then we have f of r of t times r prime t dt. So that's equal to the double integral over g, and then we have qx minus py, and then dx dy. Okay, so that's the theorem. It's an absolutely fantastic theorem. It's called Green's theorem. Named after George Green. Unfortunately, we don't have a photo of George Green, but that's his mill. That's his mill working order in about 1870 from the, that was a picture taken in 1924. Okay, let's look at a few remarks. First of all, if f is a gradient field, then both sides are 0. The left-hand side is 0 because of the closed loop property. And here, because of Clairaut. So that's an indication that it's a good theorem, right? But it's not yet the proof. And but I should say something about the proof. The proof works by looking at the small square or small rectangle. And if you look at the small rectangle and you apply this line integral here, so if this is a small rectangle, P, Q, it's F. So if these are the components P and Q, what you have is there is a part of the line integral here. This part here is actually, that gives you the py. So this gives you the py component because it's a difference between line integrals of p here and p here. P here minus p here. So that's the py, actually with a negative sign. And then the qx, the qx is the rate of change here. That gives us the qx. So if that was the region G here, we can cut it up into small pieces, and then every of these in this little piece we can use the result here. And what happens is there's some magic going on here, and that's a cancellation of the line integrals here and here. This line integral and this line integral cancel away, and this line integral and this line integral cancel away, and so the only thing which is surviving is this line integral here along the boundary. So that's the basic principle. These curls add up, all these curls add up, and that's what we write. What we write on the here. But what they do is they are actually small, infinitesimal, small work contributions of us, and they all add up, and this work cancels in the interior. Only the boundary part of the work survives. It's a pretty cool thing. And so that's kind of the intuition here. Of course, if you want to prove this, we can do that more precisely, but we are not doing that here. So let's do an insane example. I made just up right on the spot. I made up a vector field here, a little bit crazy, because we are all crazy these days. So this is a insane vector field, and also a relatively complicated curve here. It's a polygon going here, 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 here. Beautiful polygon, and so we want to compute that. Now you never ever ever want to compute this directly. It would be really insane, because you would have to parameterize each part. So you would have to parameterize 1, 2, 3, 4, 5, 6, 7, 8. This is an 8-gon, so you would have to parameterize 8 lines and compute these integrals, and you would die computing these integrals. But fortunately, we can do that almost in our head. So the answer is very easy. This is very easy with Green's theorem. So first of all, if you look at the vector field f, then when you look at Green's theorem, we have to look at the curl of f. So look at the curl of f. So this is qx minus py. So this is p, this is q. So qx minus py, you see that e to the crazy e to the thing that goes away. That's just 7. And py is also easy, that's 4, right? So that 7 minus 4, this is equal to 6. So now we know that with Green's theorem, that this line integral f dr, that's the double integral over g of the curl, which is 3 times dA. Now that's very important. If there's this constant here, we can take that constant out, and then we get 3 times the integral 1 dA. And you all should know what, when we integrate 1, what this gives. This is 3 times the area of G. And in this case, we can actually kind of get the area, right? So this is, when we look at that, if we would just take this, maybe, this is maybe the easiest thing to see here. If we take, so then we have this is minus 2, this is minus 3. So this is 3 times square root of 2 here. So the area is 3 times square root of 2. That's the length squared, and then we take away this part here, and this is if this is 1, and you can actually see this is just 2 each of them, so minus 4. So this is equal to 18 minus 4, which is equal to 14. Let's just see that a little bit differently. We can see that differently. So what we have is, we have 1 here, we have 2, we have 3, we have 4, we have 5, we have 6, right? 6, and then 1, 2, 3, 4 times 2. 8 plus 6 is 14, 2. So you see, you just can split it up into triangles. Each of the triangles we can get, and so we have that this is 14 for the area, and so this is 3 times 14, which is 42. As you know, all is the answer to everything. So let's look at the special case of Green's theorem when we have integrate over the region 1 dA. So we know this is the area. So if you have a vector field which has curl 1 everywhere, then we can write this as the curl of f dA. So let's just take a vector field which has constant curl 1. And the simplest one which you can come up with is the vector field 0x, which we already looked at. Or another vector field which we have looked at is minus y0. Right? So these are vector fields which have curl 1. Another popular one is minus yx half, which is the average of these two. They all have curl 1. So there are many of them. You can make up. We have seen this insane example last time at curl 3. You can divide it by 3. So, but what we know is if we have that situation, we take this vector field, for example. This gives us here with Green's theorem. This gives us the line integral f dr. So this shows we can compute the area very conveniently using a line integral. So we will do a lot of examples like that, but one most important example is the Rushmore example from the movie. I think we have the hardest geometric problem. It's the joke of the teacher there. It's the hardest problem in the world, right? So that's the ellipse. So x squared over a squared plus y squared over b squared is equal to 1, smaller or equal to 1. So that's the region which we are going to look at. So the ellipse here. So in this case we have a nice boundary curve C, which we know how to parameterize. So in this case C is parameterized with a curve a cosine t, b sine t. That parameterizes this ellipse. And now we just compute the f of, let's take this vector field here. So that's the most convenient one, the most popular one, because you don't have to remember any minus signs. And then f, we take this one here, and then f of r of t is equal to 0x of t, which is 0a cosine t. And then we have to compute also r prime of t. We do that here. So minus a sinus t b cosine t. And now we have to take the line integral. So we take the 0 to 2 pi, and then we have f of r of t times r prime t dt. So that's the integral from 0 to 2 pi, 0 a cosine t. Let's move this over here. Cosine t. Cosine t dotted with the velocity vector, which is here, minus a sinus t b cosine t dt. We just go here. And so that is equal to the integral from 0 to 2 pi ab cosine square t dt. And I'm not showing you again how we do the integral cosine square t dt. That's a double angle formula problem. So that's equal to when we integrate cosine square t. So this is ab times the integral from 0 to 2 pi cosine square t dt, which is ab pi. So that was the result. The ellipse area of an ellipse was appearing in that movie Rushmore, and that's the most direct computation. We cannot use polar coordinates here so easy, so we have seen in the movie that you need quite sophisticated trig substitution. It works with trig substitution, but here this is a nice example. Okay, before computers were taking over everything, there were mechanical computers, and one of the mechanical computers which were popular is the planimeter. So this is a mechanical computer, not a digital computer, but using quite basic principles, but it's based on Green's theorem. Don't have one which works, but let me just see here. So what we have is, let me just make it blue here. It has two arms, two legs. Both have the same length, maybe L. And what this defines, it defines a vector field. So at every point here we have a vector. So if the arm goes like that, let me just maybe show it like that. If the arm goes like that, then the vector field is like this. So what we do is we do at every kind of, we go like that, maybe we go like that, and so what we have is we have always a vector attached. So this is if this is the point xy, this is the vector field fxy. So this is f. If this is xy, this is fxy. So you can write down formulas for this vector field, and its magic is this vector field has curl 1. So this vector field has the planimeter vector field. At least if it's 1 here, let's just take 1 as curl 1. Constant 1 everywhere. So what happens is when we actually compute the line integral here, when we are moving along the curve like that, we are moving along the curve and we are computing the line. So what happens is you have a little wheel here which slides along, and so this line integral along C f dr is the area. So you can compute the area just by sliding along here. And this was used, for example, in medicine. If this is a tumor, you want to compute the size of the tumor, or if this is a forest, you want to know the area of the forest. And so these planimeters, you can still buy them, cost about a few $100s because it's antique, and but they are pretty cool, and they are based on Green's theorem.